Welcome to the deep dive. Today, we're taking a deep dive into a classic computer science problem, merging two sorted linked lists.
Hmm.
Now, even if you're kind of familiar with terms like pointers and nodes, maybe you encountered them before, today we're going to offer a surprisingly intuitive way to look at it.
Yeah, turn something that can seem pretty abstract into something, well, much clearer.
Exactly. Our mission for you today is really to give you a shortcut to, truly understanding this concept, hopefully give you some of those aha
Hmm.
moments.
hmm
We've been exploring some really fascinating source material that uses this brilliant real-world analogy to make this complex idea just sort of click into place.
Yeah.
What really stood out for me anyway was this clever trick involving a dummy placeholder and a tail tracker. It simplifies everything, makes the whole thing incredibly elegant, actually.
It's really remarkable, isn't it, how often these, abstract computer science challenges have parallels, really intuitive ones, in just our daily lives.
Yeah.
And this deep dive, it uses one of the best analogies I've seen, honestly, to demystify something that, yeah, can otherwise feel quite intimidating.
Okay, so let's get into it. What exactly are we trying to achieve here? What's the problem?
Okay, so imagine you're given two separate, singly linked lists.
Right, a separate list.
And the crucial detail, the key here, is that each list is already sorted, say, in ascending order.
Got it. Pre-sorted.
Your task is then to combine them, merge them into a single new sorted linked list.
One single list, still sorted.
Exactly. And importantly, you need to do this in place.
Ah, okay. What does in place really mean here?
Good question. It basically means you should do it without creating a whole bunch of new components, like new nodes for every single item. You're mostly just rearranging the existing ones.
So not making copies, you're reusing the original parts.
Precisely. Which
Yeah.
is, a super efficient approach, especially when you're thinking about memory usage. Very important.
Right. So why is this specific problem, merging sorted lists, why is it so common? Why foundational?
Well, it's a core operation anytime you need to combine ordered data efficiently. Think about database records. Maybe you have two sorted sets you need to merge.
Okay.
Or managing task queues in a system, perhaps based on priority.
Hmm.
Or even sorting really large data sets. Sometimes you sort chunks and then merge them.
Ah, divide and conquer style.
Exactly, that kind of idea. It's a fundamental skill, really, that underpins a lot of how we handle information in a structured way.
Okay, makes sense. So let's unpack this with that analogy you mentioned, the real world one.
Let's do it.
Instead of abstract lists and nodes, I want you to picture yourself at an airport, maybe baggage claim.
Okay, I'm there.
You've got two luggage conveyor belts right in front of you,
Mm-hmm.
and on each belt, suitcases are perfectly lined up, and crucially, they're sorted by increasing weight. Lightest first, then heavier, moving along the belt.
Got it. Two sorted lines of suitcases.
Right. Your mission, should you choose to accept it, is to create a new single conveyor belt. One belt. That perfectly merges the suitcases from the original two belts, keeping all of them in their correct sorted order, from lightest overall to heaviest overall.
Okay, so taking two ordered streams and making one perfectly ordered stream.
Exactly. When I first heard linked lists, my eyes kind of glazed over a bit. Pointers, nodes, nulls.
Yeah, it can sound dry.
But then this analogy came along, the suitcases, and suddenly it was like, oh, it's just really organized baggage claim.
Huh, yeah, pretty much. And zooming out a bit, this analogy is incredibly powerful because it maps almost perfectly to the linked list concepts. Let's break that down.
Okay.
So each suitcase, that's like a node in our linked list. It holds a value, right? Like its weight.
Okay. Suitcase is a node, weight is the value.
Yep, a conveyor belt itself. That's the entire linked list, the whole
Node
sequence.
chain.
Right. Now the tray, right after a suitcase on the belt.
Yeah.
Think of that as the dot next pointer.
Ah, the link. What points to the next one?
Exactly. It tells you where the next suitcase in the sequence is.
So what if there isn't a next one? End of the belt.
Good point. If that tray is empty, it signifies that dot next equals null. You've reached the very end of that specific belt or list.
Null means end. Got it.
And if the tray holds another suitcase, well, that means dot next, null. And it points you directly to the next node in the list.
Okay, that maps really well. What about building the new belt?
Right. So adding a suitcase to the new belt you're building, that's like setting the dot next pointer of the last suitcase you added. We often call that pointer new belt tail. So new belt tail dot next, suitcase.
You're hooking the new suitcase onto the end of your merged chain.
Precisely. And that last added suitcase is exactly what our new belt tail pointer keeps track of. It always points to the current end of your merge list, ready for the next edition.
Okay, this is making a lot more sense now. So how do we translate this airport scenario into the actual algorithm? How do you manage those suitcases and belts, in code?
Great question. Let's walk through the steps.
First off, you set up something called a dummy node.
Ah, the dummy node, yes.
What is that exactly? It sounds kind of fake.
Yeah, well, it is sort of temporary. Think of it as a conceptual empty start for your new merged belt. A placeholder.
Okay, not a real suitcase then.
Not a real suitcase. It's never actually part of the final merged list, but it's brilliant because it massively simplifies the setup, especially handling the very first element.
How so?
It gives your new belt tail pointer something to point to initially before you've added any real suitcases. It avoids needing special if conditions just for adding the first item.
Ah, okay. So it standardizes the process right from the start.
Exactly. It's one of those subtle but incredibly effective patterns you see in programming. A real simplification hack.
Nice. So dummy node first. What else?
You also create that new belt tail pointer we just talked about. It keeps track of the last real suitcase you've placed onto your new merged belt.
And initially,
Initially, it points right at that dummy node.
okay, dummy node setup, tail pointer pointing to it. Ready to merge.
Ready to merge. Now for the core logic, the merging loop. Imagine you have two helpers, or maybe just think of them as pointers, one at the front of each original conveyor belt.
Okay, one pointer for belt 1, one for belt 2.
Let's call them B1 head and B2 head. They're always looking at the current suitcase at the very front of their respective belts.
Got it.
Now, the rule is, as long as both original belts still have suitcases coming, so neither B1 head nor B2 head is null.
Okay, well, there's still stuff on both belts.
Your helpers, or pointers, compare the weights, the values of the suitcases they're currently looking at, the ones at the front.
Compare belt 1's front versus belt 2's front.
Yep. Then they pick the suitcase that's lighter, the one with the smaller value.
Okay, take the minimum.
Right. That lighter suitcase is then moved. Conceptually, you're just relinking its fixed pointer. Next pointer, you attach it to the end of your new merged belt using that new belt tail.
So new belt tail.next now points to this lighter suitcase.
Correct. Then, two crucial things happen. First, you advance the pointer on the original belt from which you just took the suitcase. So if you took it from belt 1, B1 head moves to the next suitcase on belt 1.
Right, you've processed that one move to the next on that specific belt.
Exactly. And second, you also advance your new belt tail pointer on the new belt to point to the suitcase you just added.
Ah, so the tail always follows the last added item. Ready for the next link?
Precisely. You repeat this, compare fronts, pick lighter, link it to the tail, advance the source pointer, advance the tail pointer.
Okay, keep doing that loop. But what happens when one belt runs out of suitcases first? Like, belt 1 is empty, but belt 2 still has suitcases.
Great question. Do you have to sort the rest?
Yeah, do you have to keep comparing or sorting?
No, not at all. And this is where the efficiency really shines. Eventually, one of your original belts will run out. B1 head or B2 head will become null.
Okay.
At that exact point, any suitcases remaining on the other belt, well, they're already perfectly sorted, right? That was our starting condition.
Oh, right, because the original lists were sorted to begin with.
Exactly. So you don't need any more comparisons. You just take the entire remaining portion of that non-empty belt and attach it directly to the end of your new merged belt. Just set new belt tail dot next to point to the head of whatever's left on the other belt.
Wow, okay, so just link the whole remaining chunk in one go.
Yep. One simple pointer assignment. This entire process guarantees you're always picking the globally lightest suitcase available from the fronts of the two source belts, meticulously maintaining that perfect sorted order throughout.
That is pretty elegant. Let's run through a quick example, maybe make it really concrete.
Good idea. Numbers usually help.
Okay, imagine belt 1 has suitcases with weights. 1 year 3, 5.
Okay, 1, 3, 5.
Then belt 2 has 2 year 4, 6.
2, 4, 6, both sorted.
Right. So how does the merge proceed? We start with our dummy node and the tail pointing to it.
Okay, now compare the fronts.
Yeah.
1 from belt 1 and 2 from belt 2.
1 is lighter, so we add 1 to the new belt. Tail now points to 1. Advance belt 1 pointer.
Correct. Belt 1's head is now 3. Belt 2's head is still 2. Compare 3 and 2.
2 is lighter. Add 2 to the new belt after 1. Tail points to 2. Advance belt 2 pointer.
Perfect. Belt 1 head is 3. Belt 2 head is now 4. Compare 3 and 4.
3 is lighter. Add 3 after 2. Tail points to 3. Advance belt 1 pointer.
Yep. Belt 1 head is now 5. Belt 2 head is 4. Compare 5 and 4.
4 is lighter. Add 4 after 3. Tail points to 4. Advance belt 2 pointer.
Keep going. Belt 1 head is 5. Belt 2 head is now 6. Compare 5 and 6.
5 is lighter. Add 5 after 4. Tail points to 5. Advance belt 1 pointer.
Okay, what happens now to belt 1?
Belt 1's exhausted. What's left on belt 2?
Just the suitcase with weight 6?
Exactly. Belt 1 is exhausted. What's left on belt 2?
Just the suitcase with weight 6.
So what do we do?
Oh, we just attach that remaining part, the 6, directly to the end of our new belt after the 5.
Bingo. No more comparisons needed.
So the final result is 1, 2, 3, 3, 4, 5 here, 6. A single, perfectly sorted belt.
You got it. That's the merge action.
Okay, seeing it step by step really clarifies the process. Now, let's think about the bigger picture here. The implications. Why is this method considered so good?
Right, the efficiency part.
Exactly. There are a couple of key reasons. First, it's time complexity. How long does it take?
Well, we looked at each suitcase basically once, right? Either comparing it or attaching it at the end.
Precisely. So if Belt 1 has N suitcases and Belt 2 has N suitcases, the total time is directly proportional to the total number of suitcases, N plus M. We write that as ON plus M.
O and N plus M. Linear time. That sounds pretty fast.
It's very fast because you're essentially just doing one pass through all the elements combined.
Okay, what about space? Memory usage.
That's the other really crucial part. Its space complexity is O1.
O1. What does that mean again?
It means you're using constant extra space. The amount of extra memory you need doesn't depend on how many suitcases you have.
But wait, we created the dummy node and the pointers like new belt tail, B1 head, B2 head.
True, but those are just a few fixed variables. It doesn't matter if you have 10 suitcases or 10 million. You still only need one dummy node, one tail pointer, 2 head pointers. The extra space needed is constant.
Okay. Because we're not creating new suitcases, just rewiring the next pointers of the existing ones.
Exactly. That's the in-place nature we talked about. You're rearranging, not duplicating. And this is incredibly valuable, especially in situations where memory is limited or very expensive.
Okay, that makes sense. But, if it's so efficient and uses minimal extra space, why wouldn't someone just, I don't know, throw all the suitcases from both belts into a big pile, sort them using some standard sorting algorithm, and then put them back on a new belt? What's the specific advantage here?
That is a fantastic question. It really gets to the heart of why linked lists are useful for certain tasks.
Okay.
If you were to dump everything into, say, a big array or list structure first, you potentially have to physically move data around in memory when you insert items or sort them. That can be slow, especially for large items or lots of them.
Right, copying data takes time.
And more importantly, sorting a combined, unsorted list of N plus M items typically takes ON plus M time using efficient algorithms like merge sort or quick sort.
Okay, log N plus M versus just N plus M for our merge.
Exactly. ON plus M is significantly faster than ON plus M, log N plus M, especially as N and M get large. With linked lists, merging involves just changing these small pointers. It's like you're just updating the addresses on shipping labels, not physically moving heavy boxes around the warehouse.
Okay. Less data movement, just pointer manipulation. It's like being a meticulous air traffic controller for suitcases, maybe. Making sure everything gets routed correctly without unnecessary shuffling.
That's a great way to put it. You ensure every single one lands in the right spot in the sequence efficiently.
Okay, so pulling it all together then, what are the absolute key things someone should take away from this deep dive?
I think there are a few core ideas.
Okay.
First, the power and, frankly, the cleverness of using a dummy node. How it simplifies handling the start of the new list. No special cases needed.
Right, the simplification hack.
Second, the importance of maintaining that new belt tail pointer. It makes adding items to the end of the growing list super efficient, always knowing where the current end is.
Always ready to append.
Third, really internalizing that idea of the next pointer as being like that tray after the suitcase. It either holds the next item or, if it's empty, null, it signals the end of the line.
The core linking mechanism.
And finally, just the elegant logic itself. Compare the fronts, pick the smaller one, link it, advance the pointers. That simple loop preserves the sorted order perfectly.
Yeah, it seems quite straightforward when you break it down like that with the analogy.
It really does.
So this merge algorithm for sorted linked lists, it's clearly essential stuff. And as we've seen these visual analogies like the conveyor belts and suitcases, they just make it so much easier to grasp and hopefully apply later.
Absolutely. It's a perfect example of how breaking down something that looks complex into relatable, manageable steps can lead you to a solution that's not just correct, but really elegant and efficient too.
And that wraps up our deep dive into merging sorted linked lists. We took a concept that, often feels a bit abstract, maybe even intimidating, and hopefully turned it into a clear visual process, All thanks to digging into some well-organized source material and that great analogy.
It really does highlight how even pretty technical concepts can click, can be understood deeply when you find the right connection, often using simple everyday scenarios.
Definitely. So for you, our listener, here's something maybe to mull over. What other complex concepts have you encountered, maybe in your work or hobbies or even just daily life,
Yeah,
that, if you found the right analogy, could suddenly just click into place, unlock a whole new level of understanding for you?
that's a great thought. Analogies are powerful tools for learning.
We hope this deep dive helps you look at information, maybe data structures, and perhaps even airport baggage claim in a new, more insightful way.